Hello, everyone. Welcome to this week's edition of the Brazilian Algebraic Geometry Seminar. Today is a pleasure to have Gaia Comaschi from IMEC UNICAMP, and she'll tell us about instanton sheaves of low charge on Fano threefold. Please, Gaia, go ahead.
Okay, so thank you very much. So hi, everybody. Today, I would like to present the work that I've been working on in these last few months with Marcos, and that concerns instanton sheaves of low charge on Fano threefolds. So here is the plan of the presentation. We will start with some preliminary material about instanton on the projective space. We will then pass to see how is it possible to generalize the notion of instanton to other Fano threefolds beside the projective space. And we will then see in greater detail what happens for instanton sheaves on quadric and cubic threefolds. So to start with, we consider instanton on the projective space. Instanton bundles were indeed originally defined on P3. And the classical, let's say, definition of an instanton bundle is the following. So an instanton bundle of charge n on P3 is defined as a rank 2 stable vector bundle with Chern classes C1 equal to 0, C2 equal to n, and such that we have the vanishing of this cohomology group. We can easily prove that instanton bundle satisfy the following properties. So instanton bundles are mu stable. The stability implies that whenever we take negative twist of an instanton, we have no global section. And using the stability and applying their duality, we can prove the vanishing of these groups of cohomology. If now we wonder how to extend the notion of instanton in order to include also not necessarily locally free sheaf, we can give the following definition that was firstly introduced by Jardim and Gargate, that states that an instanton sheaf of charge n on P3 is a rank 2 torsion free sheaf having Chern classes C1 equal to 0, C2 equal to n, C3 equal to 0, and that once again will satisfy the vanishing of these cohomology groups. So the fact that we have the vanishing of these cohomology ensures that instanton sheaves can be represented as the cohomology of linear monads of these forms. So let's now try to understand how these two definitions relate. So of course, if we have a vector bundle that is an instanton bundle in the, let's say, classical sense, it will be a locally free instanton in the sense of the second definition. Note that the converse might not hold since we are no longer requiring stability. So if we consider as a definition of instanton the second one, we can also consider strictly semi-stable instanton. Indeed, we can prove the following, that whenever we have an instanton sheaf on P3, it satisfies the following property. So if ever E is reflexing, then it is locally free. Whenever we have an instanton, its double dual is always a locally free instanton. If ever an instanton is non-locally free, then the quotient of E double dual by E is a sheaf of pure dimension 1. Every locally free instanton that is non-trivial is stable, so that in particular, since the mu stability of E is equivalent to the mu stability of E double dual, we deduce that the mu stability of E is equivalent to the fact that E double dual is the non-trivial instanton bundle. So from the definition, we understand that instanton sheaves, also the non-locally free ones, plays a really important role when we try to study the quiver moduli space of instanton, since they arise as cohomology of linear monads. It turns out that instanton sheaves also play a fundamental role when we look at the Gieseker-Maruyama moduli space of instanton. Indeed, if we consider the moduli space En of instanton bundles of charge n bigger than or equal to 1, then we have the following. So since for n bigger than or equal to 1, we have stable objects, and since the instantonic condition is open in the moduli space, then En can be considered as an upper in the projective moduli space obtained by the Gieseker-Maruyama compactification. And moreover, it is possible to prove that this space En satisfies the following properties. So it is affine, it is non singular, and it is irreducible of dimension A10 minus 3. So if now we consider its closure in the Gieseker-Maruyama moduli space, so the moduli space of torsion-free semi-stable sheaf of rank 2 and Chern classes 0 and 0, we want to see what happens in this boundary. So what happens when we move in En bar minus En. And it's exactly in this boundary that we can understand the importance of instanton sheaves. It was indeed proved by Jardin, Markuszewicz, and Tikhomirov the following. So that for any n that is bigger than or equal to 1, in this boundary, we find n irreducible components. And the generic points of each of these components is an instanton sheaf. The Gieseker-Maruyama moduli space is smooth at these sheaves, and generically, a point in these components is an instanton sheaf that has one-dimensional singularity, and that more precisely is singular along a rational normal curve of degree n. So our aim is try to understand how much of this portrait we can reproduce on other Fano threefolds. So we move now from P3 to another Fano threefold X of Picard rank 1. So remember that here the Picard has rank 1, so we denote by H the ample generator. The index Ex of X is defined as the integer that satisfies the following relation, where Kx is the canonical divisor. And calling then Rx and Qx the quotient and the remainder of the quotient of Ex by 2, so that we can write Ex in this way, we have the following definition that was proposed by Faenzi of instanton on X. So we say that an even or odd instanton bundle of charge n on X is a rank 2 stable vector bundle that has Chern classes G1 equal to 0 in the even case, equal to -1 in the odd case, with a second Chern class n, and satisfying the following. So we have these, let's say, symmetry properties. And then we have again the condition of the vanishing of the cohomology of a twist of the sheaf. So this is what on P3 was -2, so half of the canonical. Similarly to what happens in P3, we can prove that the stability and the self-duality implies that for any instanton, either even or odd, we have indeed the vanishing of all the cohomology groups of the twist of E by -Qx. So also in this case, we aim to generalize the notion of instanton to non-locally free sheaves. And to do so, we propose the following definition. So we say that on X, an instanton of charge n is a rank 2 torsion-free sheaf with first Chern class equal to -Rx. So here we have either 0 or -1, depending on the fact that the index is even or odd. The second Chern class is n, and this time the instantonic condition will be the vanishing of all the cohomology group of the twist of E by -Qx. So some preliminary property that we can easily prove for instanton are the following. So similarly to what happens on P3, whenever we take an instanton, the double dual is always a locally free instanton. Then we have the following, that it's simply due to the fact that we are considering torsion-free sheaf. So the mu semi-stability of E is equivalent to the mu semi-stability of its double dual. And we have that each instanton sheaf has homological dimension less than or equal to 1. So E is either locally free or it has homological dimension exactly equal to 1. In the second case, then since E is torsion free, it injects in its double dual, so it gives us this defining short exact sequence. So we take E, we take its double dual, locally free instanton, and we can prove that the co-kernel of this injection is a so-called rank 0 instanton. So this sheaf Q, exactly as it was the case for P3, is a sheaf of pure dimension 1 that satisfies this vanishing in the cohomology. So when we take the twist by minus QX, this sheaf has no cohomology. The sheaf Q is supported on the singular locus of E, that is therefore a curve that has pure dimension 1. And from this short exact sequence, we can compute that this curve will have degree equal to the charge of E minus the charge of E double dual. Note that conversely, whenever we start from an instanton bundle E and a rank 0 instanton Q, and we take a surjection from E to Q, then the kernel will be an instanton sheaf that will be singular along the entire curve that is the support of the sheaf Q. Usually this operation, so taking this epimorphism, this operation is called an elementary transformation of E by Q. Okay, let's now see in greater detail what happens on quadrics and cubic threefolds. So for the moment, we suppose that X is a smooth quadric hypersurface in P4. So X is the only Fano threefold of index 3. So that in this case, following our definition, we have that an instanton on X will simply be a rank 2 torsion-free sheaf with first Chern class equal to -1, and such that the twist by -1 of the sheaf E has no cohomology. So on X, we can prove that for instanton bundles, so locally free instanton of rank 2, either we have mu stability or we have mu non-stability, and in which case we have that E is the trivial bundle, so the trivial bundle with furniture class -1, that is simply the direct sum of the structure sheaf plus the structure sheaf twisted by -1. So in other words, we have that the minimal charge of a semi-stable, therefore strictly stable instanton bundle is C2 equal to 1. So the instanton bundles that have this charge, so the minimal charge, the stable instanton bundle of minimal charge, are usually referred to as a spinal bundle. So the moduli space of the spinal bundle just consists of a point, simply because of the fact that we just have a unique isomorphism class of these bundles. And moreover, the spinal bundles can always be obtained starting from a line L on X and taking a non-zero extension class in this X group. So in other words, for every line, we have this one-dimensional vector space, we take a non-zero extension, and therefore we have a short exact sequence of this form, whose middle term will be a vector bundle, an instanton bundle of charge 1, therefore the spinal bundle. So from this, we also understand that the projective space of global section of the twist of S by 1 is a three-dimensional projective space that is isomorphic to the Hilbert scheme of lines on X. So S can always be constructed from L, from a line on X, and conversely, every line on X can be realized as the zero locus of a global section of S twisted by 1. So let's see what happens when we pass to instanton of charge 2. So we leave the minimal charge. In this case, we have that an instanton bundle of charge 2. For an instanton bundle of charge 2, the twist by 1 always admits global section, and a global section always vanishes along a curve Z that is locally Cohen-Makoli, that has degree 2, and that necessarily consists either of the union of two disjoint lines or of a double line having genus -1. So another way to say this is that an instanton bundle of such a kind always fits in a short exact sequence of this form. So this is just the morphism that corresponds to the global section of the twist. And Z will be the co-kernel, so the ideal sheaf of Z is simply the co-kernel of this global section. So from this short exact sequence, we can compute the following. So we can compute that the x1 of EE has dimension 6, the x2 of EE x dimension 0, but this means that the Gieseker-Maruyama moduli space of semi-stable sheaf of rank 2 and Chern classes -1 to 0 is smooth at E and has local dimension 6. So note that conversely, whenever we start from a locally Cohen-Makoli curve Z on X that has Hilbert polynomial to m plus 2, which implies necessarily that either Z is the union of two disjoint lines or Z is a double structure on a line having genus -1. Whenever we have a curve of such a kind Z and we take an extension E in these X groups, an extension does not vanish on none of the two of the components of Z, then this extension class will define a short exact sequence of this form. And because of this assumption on E, so because of the fact that we are requiring that E does not vanish on none of the components, this middle term will be a vector bundle, and computing cohomology, we can verify that E is indeed an instanton bundle having charge 2. So once that we have understand what happens for instanton bundles, let's try to move to the non-locally free case. And so let's try to understand what happens for non-locally free instanton sheaf of charge 2. So the mantra when we deal with instanton sheaf is always try to understand what is the double dual. So since we are interested in moduli problems, we consider semi-stable instanton sheaf because these are the only one that appears in the moduli space. So for a semi-stable non-locally free instanton sheaf of charge 2, the double dual must be an instanton bundle. It must be semi-stable. The charge of the double dual must be strictly lower than the charge of E. Hence, we just have one possibility, so that the double dual must be exactly the Spinal bundle. So E double dual is our Spinal bundle, and from this we understand that E fits in the following short exact sequence. So this is just the standard inclusion of E in E double dual and the co-kernel of this inclusion. So our rank 0 instanton this time will be the structure sheaf of a line on X. So this line L will be exactly the singular locus of the sheaf E. So from this short exact sequence, using the fact that the moduli space of Spinal bundle is of course smooth since it is just a point, we can compute the following. So we can compute that x1 EE is again equal to 6, x2 EE is equal to 0, so that once again we can state that the Gieseker-Maruyama moduli space is smooth and has dimension 6 at E. So summing up, what we have found is that these moduli spaces, both at instanton bundles and instanton sheaves, is smooth of dimension 6. This means that each component passing through these sheaves must have dimension 6. So it is natural to try to understand whether the components in which the instanton sheaves lives is exactly the instanton bundle component. So whether these two components that we found it coincide. And in order to determine this, so to answer to this question, we study if ever an instanton, a non-locally free instanton deforms to an instanton bundle. And our strategy to face this problem is to try to understand the deformations of the curves that corresponds to instantons. So we take our defining short exact sequence. It was recall of this form. We twist by 1 and we take global section. So here we have dimension 4. Here we have dimension 3. So dimension 2, not dimension 2. So we cannot have an injection. Therefore, E twisted by 1 must have global section. So let's try to understand which are the curves that are the zero locus of the global section of E twisted. So more precisely, let's try to understand when a section of the twist of the spinal belongs to the image of this inclusion. So for a section, global section S of such a kind, we get a commutative diagram of the following form. So here in the central row, we have the defining sequence of E, with here the singular locus. Here we have the sections of S twisted by 1 coming from a global section of E twisted by 1, because of the fact that S, I denote both sections, so either the section of E and its image in S0, S1, I name both of them by S. So because of the fact that this comes from a global section of E, here we must have 0, so that we can complete this diagram. So we will have here that the co-kernel of S will be the ideal sheaf of a line, since S is the spinal bundle. Therefore, this last row, in this last row, we will have a short exact sequence where we have a surjection of the ideal sheaf of a line. Here, the structure sheaf of the singular locus of E. Therefore, the co-kernel of the global section of E twisted by 1 will be the ideal sheaf of a scheme Z that contains the line L prime, because it fits, so it must inject in EL prime. So looking at the third row of this commutative diagram, that I rewrite here like this, we understand that every global section of E twisted by 1 vanishes along a curve Z that, because of the instantonic condition, must be locally co-Makoli, because indeed that we have a sheaf that has a homological dimension 1. And since we have this short exact sequence, we deduce that Z is supported on the union of L prime and of L. So we can prove that we can characterize more precisely the family of curves that we obtain in this way, proving the following. So when E is a non-locally free sheaf, instanton sheaf of charge 2, then each global section of the family of curves that are zero locus of global section of the twist of E by 1 is a one-dimensional family of curves of the form L prime union with L L prime that varies in a ruling of the same quadric surface containing L. So we are considering, in other words, we are taking a smooth hyperplane section of X that contains the line L, so the singular locus of our instanton sheaf, and then we are considering the entire ruling that contains this line L, and all these one-dimensional family of curve will simply be given by the line L fixed, and then we make all the other line of the ruling varying. So what we obtain is a P1 of curves that are either our line L counted with multiplicity 2 or a union of two disjoint line. So this time, our instanton sheaf will arise from an extension class in this X group. But since we have singularity all along the line L, this section will be of the following form. So it will vanish necessarily along the entire L. In order then to determine whether we can deform E to a locally free instanton, we try to understand the deformation of the curve Z, and we do the following. So first of all, we construct a flat family over the affine line. We construct a flat family of degree 2 curves over the affine line, whose general element is the union of our line L, because this is the singular locus of E, and of a second line disjoint from L. And the central fiber of this family is our scheme Z. We take then a non-zero element ST in this X group, and this element must be such that for any t different from 0, ST is nowhere vanishing, and for t equal to 0, S0 is exactly equal to E. So in other words, we have a one-dimensional family of extension, and the middle terms of this extension, so of this short exact sequence, is a family over A1, for which the general element is therefore an instanton bundle, and the central fiber will be exactly our instanton sheaf. So this will be more or less the strategy that will be mainly adopted in order to understand the deformation of instanton sheaves. So trying to understand if it's possible how we can move and deform the curves corresponding to instanton sheaves in the Hilde schemes. If now we pass to the question of smoothness and irreducibility of the moduli space, it was proved by Ottaviani and Zurek that the moduli space of instanton bundles of charge 2 is smooth, irreducible, and has dimension 6. So the idea of the proof is the following. For instanton bundles, exactly as it happened for instanton sheaves, all the curves that are the zero locus of global section of the twist of E belongs to, are contained in the same hyperplane section of our quadric X. This means that we can define a morphism from the moduli space of instanton bundle to this open. So here we are considering the dual projective space. We are throwing out the dual hypersurface. So in other words, here we have the family of smooth hyperplane section of X. So this is just the morphism that sends E to the hyperplane section that I named here QE. And what we have is that this morphism is surjective, and the fibers are two copies of two smooth two-dimensional opens in P2. So more precisely, if we take an hyperplane section Q here, the fiber consists of the base point free linear systems of time to 0 on Q. In other words, we take an hyperplane section and we fix one of the two rulings, and then we consider copies of lines in these rulings. So a similar approach can be used in order to determine the reducibility of the family of non-locally free instantons. Indeed, we can prove that we have the following. So the family, so instanton sheaves that are singular along the line are parameterized by an irreducible 5-dimensional family that is contained in the closure of the moduli space E2. And this moduli space, so this 6-dimensional component, is smooth along each of our non-locally free instantons. So summing up, we have just found one instanton components, and the instanton components, the 6-dimensional instanton components, is smooth along the entire family that parameterizes non-locally free instanton sheaves. So how to prove this? We saw in a previous proposition that also for instanton sheaves, all the curves that are zero locus of global section of the twist of E are contained in a same hyperplane section of our quadric X. Therefore, once again, we can define a surjective morphism of this form. So here we are sending sheaf E to the quadric QE that contains all the curves Z constructed in this way. Since all these quadric surface must be smooth, the image of this morphism lie in the open parametrizing smooth hyperplane section. This time, the fibers will be two copies of P1 because we are no longer taking a base point free linear system. This time, the linear system has a base point, since remember that when we have a non-locally free instanton, all these curves contains the line that is the singular locus of the instanton sheaf. So here, in order to understand the fiber, we fix our hyperplane surface, we fix the ruling, and then we fix a line in the ruling. Once we have done this, all the other curves will be this line plus all the other lines in the ruling. We get a complete description of the moduli space of semi-stable rank 2 torsion-free sheaf of Chern classes -1 to 0. And what we find is that this moduli space consists of our 6-dimensional component, that is the closure of the instanton component, F, and of another irreducible component that has dimension 10. So these second components that here I denote with C2, in this component, a general point corresponds to a sheaf that has 0-dimensional singularity. So more precisely, it is singular along a 0-dimensional scheme of length 3. Such a sheaf F, so a general point in these other components, is a stable torsion-free sheaf that fits in a short exact sequence of this form. So it differs from its double dual just at a point. And this double dual is a stable reflective sheaf with the following Chern classes. So we have first Chern classes -1, second Chern classes 2, and third Chern classes still 2. And this reflective sheaf is singular along 2 points. So this is what causes our third Chern class to be equal to 2. So we can still understand this reflective sheaf by looking at the curves that are zero locus of the global section of the twist of the sheaf. So what we have this time is that when we twist by 1 this sheaf and we take global section, this global section will vanish along a plane conic, so a plane section of X. This means that F double dual arises from a non-zero class in this extension group. And in particular, doing the same trick, so obtaining the commutative diagram of this form, we can see that in this way, a global section of a sheaf with a zero-dimensional singularity will vanish along a curve that will be supported on C2 plus a point, and this time we won't therefore have a locally coherent Makoli curve because of the fact that Z is defined by this short exact sequence. We see that we have an embedded point, and once again the fact that we have a non-locally coherent Makoli curve is what causes the instantonic condition to fail. We can prove that these reflexive sheaves, so the reflexive sheaves F double dual, belongs to a 6-dimensional irreducible family of reflexive sheaves, that a sheaf in this family as a 2-dimensional family of, for such a sheaf, the space of global section of the twist as dimension 3. Therefore, we can associate to such a sheaf a 2-dimensional families of conics that are obtained as zero locus of global section. And all these conics are just plane section of our quadrics. We can prove that, moreover, we can give a nice characterization of all of these 2-dimensional family of curves associated to these reflective sheaves. Indeed, for each E in this family, we have a unique line in P4 that is contained in all the planes spanned by the conics that are of this form. So, as usual, the zero locus of a global section of the twist. In this way, we can describe a birational morphism from our moduli space of reflexive sheaf to the Grassmannian of line in P4. We are just taking a sheaf E and mapping into LE, so this line LE that meets all these conics. And these maps is nothing but the blow up of this Grassmannian along the family of lines on X. And what do we find in the exceptional divisor? Well, in this exceptional divisor, we have reflexive sheaves for which the conics, the associated conics will all be reducible, and we will have therefore a P2 of conics, all of the form a line fixed and a second line varying. So from this proposition, we can deduce at first the irreducibility of this family of reflective sheaf, and consequently of the family of sheaves of the components of sheaves with a zero-dimensional singularity. We can now pass to the case of cubic threefolds. So we now consider a smooth cubic hypersurface in P4. This time, a cubic hypersurface X is a Fano threefold having index 2. Hence, an instanton on X is a rank 2 torsion-free sheaf that will have first Chern class equal to 0. And once again, the instantonic condition is nothing but requiring the vanishing of all the cohomology of E twisted by -1. As usual, since our main aim is the study of moduli, we just focus on semi-stable objects. And we have that for instanton bundles, we have either, for semi-stable instanton bundle, we have either stability or strictly semi-stability just in the two following cases. Either we have the trivial bundle, so the case of charge equal to 0, or the case of charge equal to 1, in which E always admits a global section and a global section vanish along the line on X. So this global section will be what prevents our sheaf E to be stable, because it what destabilizes E, and E therefore always arises from an extension of the real sheaf of a line that is a rank 1 instanton on X by the structure sheaf of X. From this, we deduce that for a stable instanton, the minimal charge is equal to 2. And our main aim is to understand the behavior of instanton of charge less than or equal to 3. And it turns out that these sheaves always correspond to elliptic curves on X having degree 3 plus k. We can indeed prove that if we have an instanton bundle that has charge less than or equal to 3, then the twist by 1 always admits a global section, and each global section vanish along a curve of such a kind, so a curve with a Hilbert polynomial 3 plus kn. So here, for example, if E is the trivial bundle, this will just be the Koszul resolution of the ideal of a plane cubic. So what we can highlight is that whenever the charge is less than or equal to 2, a general global section of E twisted vanish along a smooth curve. And then we can also remark that for k equal to 2 and 3, in order to have stability, we might ask, we need to ask to the curve Z to be non-degenerate. Otherwise, when we twist by -1 this short exact sequence, we will have here H0, IZ1 different from 0, hence we will have global section of E that will destabilize the entire sheaf E. Okay, the moduli space of instanton bundles of minimal charge 2 had been studied by several authors. So let's recall here some of the main results concerning this moduli. It was proved by Markuszewicz, Tichomiron, and Iliev that E2 is smooth, irreducible, and have dimension 5. Looking at the correspondence between instanton of charge 2 and elliptic quintics, it is possible to prove that the open parametrizing smooth non-degenerate elliptic quintics has, at least locally in the TEL topology, the structure of a P5 bundle over E2. So in this way, we obtain a 5-dimensional irreducible scheme and a 10-dimensional irreducible scheme parametrizing the elliptic quintics that corresponds to instantons. Later, Drouel proved that the Gieseker-Maruyama compactification of this moduli space is, of course, irreducible and of dimension 5. It is the entire compactification is smooth, and it is isomorphic to the blow-up of the intermediate Jacobian of X along the Fano surface of lines. So the key ingredients of these results are the following. So the fact that E twisted by 1 is globally generated, which ensure that a general global section of this twist vanish along a smooth elliptic quintic. Then we have the fact that the Hilbert scheme of elliptic quintics is smooth at smooth elliptic quintics, and in this way we can deduce the smoothness of the moduli space of instanton of charge 2. Then the irreducibility of this Hilbert scheme that parametrizes the smooth non-degenerate elliptic quintics implies the irreducibility of the moduli space E2. If now we pass to the case of charge 3, we ask the same question. So what can we say about the smoothness, and what can we say about the irreducible components? Well, it turns out that The same strategy this time is not that effective, because this time the twist by one is no longer globally generated, so it's not necessarily globally generated. So we can no longer state that when we take a general global section of the twist by E, we get a smooth elliptic sextic. And also, if we just restrict to sheaves that correspond to smooth elliptic sextics, we don't get that much information, because proving irreducibility of components of these Hilbert schemes reveals, at least to me, quite troublesome. One of the main reasons is that now we are dealing with curves that are no longer projectively normal, so they are not as well behaved as for the case of degree less than or equal to 5. And so we try to construct components of the closure of E3 in other ways. And the ways that we adopt is studying non-locally free instantons and their deformation. So what we find is the following. We have that if E is a semi-stable non-locally free instanton of charge 3, then up to replacing E by a representative, an appropriate representant of its S-equivalent class, we might suppose that either E double dual is a stable instanton of charge 2, so that the quotient of E double dual by E will be the structure sheaf of a line that will be then the singular locus of E, or otherwise the other possibility is that E double dual is the trivial sheaf, so 2 copies of OX, and this time this quotient will be a rank 0 instanton of degree 3. So here from now on, I call rank 0 instanton of degree D rank 0 instanton for which the curve that is its support simply has degree D. Okay, so let's try to see what happens for the first family of these instanton sheaves. So if E is an instanton for which the double dual is a locally free instanton of charge 2, then we have the following. We have that the family parametrizing sheaves of such a kind is irreducible and has dimension 8. For a sheaf E of such a kind, the twist always admits global section, more precisely the space of global section has dimension 4, and a general global section of this twist will vanish along an elliptic sextic that will be the union of smooth non-degenerate elliptic quintic plus the line that is the singular locus of E meeting the elliptic quintic at a point. We can then compute these the dimension of these two S groups. So we can compute that x1 EE is 9, x2 EE is 0. So our moduli space is smooth of dimension 9 at E, and then prove that a general deformation of E is a locally free instanton that moreover can be corresponds to a smooth elliptic sextic. So from this we deduce in particular that this component, this family must be contained in a unique irreducible component of this closure, since this has dimension 8, the local dimension is 9, and the moduli space is smooth. So we can just have unique irreducible components that contains this 8-dimensional family. So the idea of the proof is the following. The basic step is, as usual, taking the inclusion in the double dual. The co-kernel of this inclusion we know to be the structure sheaf of the line that is the singular locus of E. From this short exact sequence, just using the fact that the moduli space of instanton of charge 2 is is smooth, we can compute these 2 dimensions. So we can compute that the local dimension is 9 and that we don't have obstruction. Then, as usual, with twist by 1, we take global section, and since here we have dimension 6, here we have dimension 2, once again, we cannot have this vector space equal to 0, so we always have a global section. As we did for the case of quadrics, we try to understand when a global section comes from the image of this inclusion here. And we have that if ever this happens, so a global section S here coming from this vector space will vanish along an elliptic quintic Z prime that will meet L at a point. So we have a commutative diagram exactly as we had in the previous case. So the defining short exact sequence with E double dual, the global section of E double dual that therefore will vanish along an elliptic quintic Z prime. Since this global section comes from a global section of E1, here we can complete in this way the diagram, so we can put here OL. Therefore, the co-kernel of this global section will be of the form ideal sheaf of a scheme Z twisted by 1, where Z will be a scheme containing Z prime. So since if these two are disjoint, we don't have epimorphism, we understand that our scheme Z will be must be an elliptic sextic, that is the union of the elliptic quintic Z prime plus the line L, and these two must meet at a point. In other words, E twisted arises from an extension class in this group, and this class, since we have a singularity along the entire line, have to vanish along the entire line L. And also in this case, the strategy in order to understand the deformation is to prove that we can, that the curve Z can be smoothed. So we prove the existence of a flat family over A1 whose general fiber is a smooth elliptic sextic and whose central fiber is the union of L with Z prime, so Z. And then we take an element in these Z groups such that for t different than 0, ST is nowhere vanishing, and such that S0 is exactly the extension E that defines our sheaf E. In this way, we describe a family over E1, a flat family, for which the general element is an instanton bundle associated to a smooth elliptic sextic, and for which the central fiber is exactly our sheaf E. And in this way, we see that a general deformation of E is an instanton bundle corresponding to a smooth elliptic sextic, and by semi-continuity, we still have the vanishing of this X group. In the case where the double dual of a non-locally free instanton is trivial, then this quotient is a rank 0 instanton supported on a curve of degree 3, then in other words, rank 0 instanton of degree 3, and it must belong to one of the following family. So either we have a rank 1 torsion free sheaf on a plane cubic having a rank 1 and degree 3 torsion free sheaf on a plane cubic satisfying this vanishing in cohomology. So let's say if generally we consider smooth plane cubic, we are just taking line bundles that does not come from collinear points. Otherwise, we can have a degree 2 line bundle on a twisted cubics, or once again, extension of rank 0 instanton of lower degree. In the case of instanton sheaves that are singular along twisted cubics, we have more or less the same that happens for instanton that are singular along the line. So we have again a irreducible a-dimensional family. We have again that to each sheaf we can associate a three-dimensional family of locally Makoli curves that this time will be union of the twisted cubic, that is the singular locus, plus a plane elliptic curve that meet the twisted cubic at point. Once again, we can compute the dimension of these S-groups, and states that a general deformation will be an instanton bundle that correspond to a smooth elliptic sextic. So the idea of the proof is the same. At first, we compute the dimension of this X that tells us the local dimension and the fact that we don't have abstraction. And then we show that we can smooth out these curves, the curves obtained in this way, to a smooth elliptic sextic. So in when we study non-locally free instanton of charge 3, we meet the first example of a non-locally free instanton that does not deform to instanton bundle. Indeed, when we look at instantons that are supported on elliptic cubic, we have the following. So we have the existence of a 9-dimensional irreducible family of sheaves that are singular along a plane cubic C3 and that are kernels of epimorphism of this form, where L is a degree 3 rank 1 sheaf on the plane cubic C3. So for a general point, we have an instanton sheaf of charge 3 for which we have local dimension of the moduli space 9, we don't have obstruction, and a general deformation is not an instanton, because here we are already fielding all the available dimension, because our family has dimension 9. A general element in this family is an instanton for which a global section of the twist will once again vanish along a locally cohem curve Z of degree 6 and of arithmetic genus 1, and then will fit in this short exact sequence. So it's like saying that we can consider its ideal sheaf twisted as an elementary transformation of the ideal sheaf of a plane cubic by a degree 3 line bundle on a plane cubic. And we have a codimension 1 family of sheaves that are not instanton, because the corresponding rank 0 sheaf does not satisfy the instantonic condition. So, for example, if their singular locus is a plane cubic, they are simply degree 3 line bundles arising from 3 collinear points. So sheaves in this codimension 1 family are not instanton, and the curves that we associate to these sheaves that are 0 locus of the section of the twist, this time are still curves of degree 6 arithmetic genus 1, but that will not be locally cohem-Makoli. Again, the locally cohem-Makoli is what is linked with the instantonic condition, and more precisely, this curve will be of the form C3. So this is the plane cubic that is the singular locus of the sheaf. Then we have another plane cubic that is whose linear span is a plane that meets the span of C3 along a line, and then we are embedding the 3 points that are the intersection of this line with the cubic X. And this sheaf E belongs to a 12-dimensional component of the moduli space, whose general point is a stable rank 2 vector bundle that arises from an extension in this X group, where C3 prime and C3 second are two disjoint plane cubic on X. So the general deformation of this sheaf is still a vector bundle, but not an instanton. So in this way, we have founded a second component whose general point is still a vector bundle, but not an instanton. Okay, that's all. Thanks for the attention.
Thank you very much, Gaia. Are there any questions or comments? Okay, just to make sure you understand. So in the end, you get the case of cubics. You get these three components, and you have one of the components, the one that comes from telemetry transformation on the elliptic curves of degree 6, I guess, that intersects both components of locally free sheaves.
Yes. So you have the components coming from, let's say, two disjoint elliptic cubic. The components, the locally free components coming from smooth elliptic sextic, and then the instanton sheaf components that intersect both of them. When your rank 0 sheaf move becomes degree 3 bundle coming from 3 collinear point, you are moving to the non-instanton components because you lose the vanishing of the cohomology. And when the curve become degenerate, you are moving to the instanton component.
Okay, thank you. Are there more questions? Okay, so let's thank Gaia again for today's seminar.